population function, P of t equals P naught b to the t, indicates a population that grows according to an exponential base b. Remember that b is going to be 1 plus the growth rate. B is the growth factor. I believe in some previous material we used a for the growth factor, but we also have used the form P naught b to the t. So that we have an initial population times a growth factor raised to the t power. We also have this form, P of t equals P naught e to the kt. Now these two forms are equivalent, just as are all the other forms. Remember, we could also have talked about a P naught times 2 to the kt form. Okay, but the P naught e to the kt form is going to be the most standard form for an exponential. Now, how is b related to k? P naught is obviously going to be the same in both equations. T is the same. The only thing that's different is we got a k here up in an exponent and a b here down in a base. How are those two parameters related? More specifically, if we have this form, P naught times b to the t, for example, 10 million population times 1.03 to the t, reflecting a growth rate of 0.03, growth factor of 1.03, what k value would correspond to that situation? Well, if these two are going to be the same, then b to the t must be the same as e to the kt. So we could write e to the kt equals b to the t, and it's a simple enough matter to use natural logs to solve this. We take the natural log of both sides. The natural log of e to the kt is just kt, the natural log being an inverse function of e. And the natural log of b to the t is t times the natural log of b. So we solve this. The t's, of course, divide out, and we end up with k equal to the natural log of b. Once more connecting this with the growth factor and growth rate ideas that we've looked at before. Again, k is the natural log of b. If b happens to be less than 1, that would correspond to a growth rate that's negative. For example, if we're in a population losing situation or a radioactive decay, b might be 0.93, which means that we're going to be taking powers of 0.93 in our calculations here. Now if b is less than 1, okay, if b is less than 1, k is the natural log of b, and k as a result is going to be negative. Because remember, when we looked at the graph, we saw if a number is less than 1, it's got a negative natural log. So that k is negative in this case. So in the case of exponential decay, our value of k is going to be negative. Your textbook says that k is positive, and we put a negative sign in front of it. And we're really saying the same thing, but personally I don't like the idea of having two different cases where you have one phenomenon. I don't separate decay from growth. This is just growth by a factor, at a negative rate by a factor less than 1, which gives us a negative value for k. If b is greater than 1, k is positive, as we saw from the graph. And if b equals 1, of course, k equals 0, and we don't have any growth anyhow in that case.